1. A very massive star is born. Black holes can form from the remains of very massive stars. These stars begin their lives when a huge cloud of gas and dust in space collapses under gravity. As the cloud contracts, its center becomes hotter and denser. Eventually, the temperature becomes high enough for nuclear fusion to begin. The star then produces enormous amounts of energy and becomes stable because the outward pressure from its energy balances the inward pull of gravity. 2. Nuclear fusion keeps the star alive. During most of its life, the star produces energy through nuclear fusion. For example, hydrogen to helium plus energy. The energy produced by fusion pushes outward, while gravity pulls the star inward. These two forces are approximately balanced. As the star gets older, it can fuse heavier elements, eventually producing elements such as carbon, oxygen, neon, silicon, and iron in different stages. The star's structure can become layered, with different elements undergoing fusion in different regions. 3. The star runs out of usable fuel. Eventually, the star develops an iron-rich core. This is a critical stage because fusing iron does not provide the energy needed to support the star against gravity. The star therefore loses its ability to maintain the balance between outward pressure and gravity. Gravity begins to win. The core starts collapsing extremely rapidly, potentially within a fraction of a second. 4. The core collapses, and a supernova occurs. When the core collapses, the material becomes extraordinarily dense. The collapse can produce a huge explosion called a core collapse supernova. The outer layers of the star can be thrown violently into space. A tremendous amount of energy is released, and the explosion can briefly make the star extremely bright. However, the supernova does not mean the entire star disappears. Its central core can remain behind. 5. The remaining core collapses further. What happens next depends strongly on the mass of the remaining core. If the core is not massive enough to continue collapsing, it may form a neutron star. But if the remaining core is sufficiently massive, its gravity becomes too strong for known forms of pressure to stop the collapse. The core becomes smaller and denser as gravity compresses it. 6. An event horizon forms. As the core becomes extremely compact, something remarkable happens. The gravitational field becomes so strong that there is a boundary beyond which escaping would require a speed greater than the speed of light. This boundary is called the event horizon. The event horizon is not a solid surface. It is essentially a boundary in spacetime. Once something crosses it, it cannot send information back out to a distant observer. 7. The central region and the singularity. According to classical general relativity, continued collapse leads toward a point or region called a singularity, where the mathematical description predicts extremely large density and space-time curvature. However, scientists do not know exactly what physically happens at the center of a black hole. Our current theories of gravity and quantum physics are incomplete in this extreme environment. A future theory of quantum gravity may provide a better description. So it is more accurate to say that classical physics predicts a singularity, rather than claiming that we completely understand the physical center. The black hole remains. H3. After formation, the black hole can remain in space and interact with its surroundings. It can pull nearby gas and dust toward it, orbit with other stars, merge with another black hole, grow by absorbing matter, produce powerful radiation from material in its surrounding accretion disk. Importantly, a black hole does strong not simply suck everything in from a huge distance. Objects must come sufficiently close, or have the right trajectory, for the black hole to capture them. P. Astronomers cannot directly see the black hole itself because light cannot escape from inside its event horizon. Instead, they detect its effects on surrounding matter, stars, and even gravitational waves. H3. The complete process in one line. Gas and dust cloud, massive star, nuclear fusion, fuel runs out, core collapse, supernova, Massive core continues collapsing, event horizon forms, black hole. H3. Important point. Not every star becomes a black hole. Our Sun, for example, is not massive enough to end its life as a black hole. It will eventually become a white dwarf instead. Also, black holes can form through other processes, including mergers of compact objects, and possibly the collapse of extremely massive objects in the early universe.